And 13.2 is Boyle's law and what we call the combined gas law. So yesterday we worked with Charles and Guy Luzac. Today we'll take a look again, very similar gas laws, Boyle's and they're combined. All right, well, starting right off here. Boyle's law. So yesterday we worked with Charles's law. Charles looks at temperature and volume, and he says they're directly related. When one goes up, the other goes up. You bring up the temperature, you're going to bring up the volume. Then we took a look at Guy Luzac. And Guy Luzac worked with pressure and temperature, and the same thing was true. They're directly proportional. When one goes up, the other goes up. More pressure means more temperature. Less temperature means less pressure. Well, Boyle looks at pressure and volume. Boyle looks at pressure and volume and finds that they are inversely proportional. Which again, it's been a while since you had some algebra. Inversely proportional means when one goes up, the other goes down. All right, me and my diagrams. Love to draw. Five dots, and yeah, that's going to be important. 5 dots. Don't want to change the number of dots. We'll call this 1 liter. So it's our volume. That area is 1 liter. And we'll just say it's 100 kilopascals. You know, we learned yesterday kilopascals is a pressure. It's a unit of pressure. And that's actually a very normal pressure. So when I say normal, you know, we walk outside, we feel 1 atmosphere of pressure kind of weighing down on top of us. And so that's just normal, right? That's what we're used to feeling. We don't really know a whole lot different. 1 atmosphere is 101 kilopascals. So this is really close to just normal pressure, what we feel every day. We probably would not feel a difference between 100 kilopascals and 101 kilopascals. Just if we walk outside. So might be 100 kilopascals in this room right now. So to draw pressure, we kind of draw these little molecules bouncing off the walls, because that's kind of what pressure is. And these guys are flying around inside of there, banging off things, banging off each other, hitting off the walls. And that's kind of what pressure is. We're measuring how often and how hard these gas molecules run into the wall. That's basically what pressure is. Well, Boyle's law if we reduce that pressure, if we reduce that volume, sorry about that, Again, got to make sure I got 5 dots over here. I got to make sure I've got my 5 dots over here. Can't change the number of dots. This is half the volume. Guess what? Inversely proportional means 0.5. Yep, 0.5. So we had 1 liter. Now we're down to just half a liter because pressure and volume are inversely proportional. When the volume goes down, the pressure goes up. So there are some big old long lines now. These guys are just going all over the place. Man, look at all this crazy. I mean, there's a ton of pressure there. We doubled the pressure. It's like 2 atmospheres of pressure. You'd feel that. You'd feel that. Man, that's twice as much pressure as what I'm used to.
So this like, like the difference between like a car tire and you put air in it and it becomes harder.
Yeah, actually, car tires. Yeah, actually, exactly right. Car tires are about 2.5 atmospheres inside of them. Yep. So yeah, this would be not even quite. This would be I don't want to call it a flat tire, but it'd be flatter than what you want in your car. You probably want about 250 kilopascals in your car tire. So yeah, yep. This is what we're talking about. Car tires measure pressure in your tire. Absolutely. All right, I know you guys are dying to get to the math part of it all, right? We draw a picture. You guys excited about that, but what you're really excited about is the math. Hey, it looks a little bit different than yesterday, doesn't it? Because pressure and volume are inversely proportional. We don't have anything on the bottom. It's just P1 times V1 is equal to P2 times V2. Makes it a heck of a lot easier. Let's take a look at an example of this.
Is that really aesthetic?
Anesthetic. It's like when you go in for a surgery, the doctor puts you to sleep. That's an anesthetic. All right, so this is a lot of what this chapter looks like. You guys started to realize that already. Nitrous oxide, N2O, is used as an anesthetic. The pressure on 2.50 liters N2O changes from 105 kilopascals to 40.5 kilopascals. If the temperature does not change, what will the new volume be? All right. Well, again, guys, take an extra minute and find your variables in this. Don't try to do a word problem. Word problems stink. Let's make it a math problem. So 2.5 liters, that's a volume. Changes from, so when we have 2.5 liters, we're starting, we have 105 kilopascals. So our starting volume is 2.5 liters. And it changes from means we started at 105 kPa. Volume, 2, that's what we're asking, right? What will the new volume be? New volume, that means volume 2. We don't have that yet, question mark. Pressure 2, it changes from 105 kPa to 40.5 kPa. So that's our second pressure. All right, so hey, there we go. We've eliminated all the words. We're left with just numbers. Now it's a math problem and not a word problem. Hopefully, just by seeing the variables that you have, you can figure out what the formula is. Boyle's law. Hey, again, something else you should really get in the habit of doing. Not just for this class, but I'm telling you, not just for science either. Like, this is good in accounting, business, medicine, all that stuff. It is good to show your work, isolate your variables. We're looking for V2. How do we get V2? We're going to get P2 out of there. Divide both sides by P2. That's an I. That's weird. Hey, there we go. Before we put any numbers in there, numbers just get in the way. They just get confusing. We've set our problem up. We say, hey, if you want V2, this is how you get it. Now we can put in our numbers. Again, the way that we got that is we wanted to get V2 on a side by itself. Right now it's multiplied. The opposite of multiply is division, so I divide the P2. All right, pressure number 1. And just look right up here and get that. 105 kPa, guys, you have to put units. Absolute imperative you put units. I'm not going to give you many points at all if you turn in a homework without units. So absolute must, 105 kPa, volume number 1, 2.50 liters. Divided by pressure number 2, 40.5 kPa. Now we're ready to compute. (105 times 2.50 divided by 40.5. 3 significant figures, 3 significant figures, 3 significant figures. So 6.48. Those are my 3 significant figures. The 1 afterwards is not enough to round up. Kilopascals cancels out. Kilopascals cancels out. There he is. Canceled out. We're left with just liters, which is good because we're looking for volume. You'd want liters because that is a measure of a volume. Finally, something I like to do. I'm in no hurry with these problems. Let's see here. My pressure went down. They're inversely related. So if my pressure goes down, I'd expect my volume to go up. We started at 2.5, we ended at 6.48. Yeah, definitely went up. Makes sense, everything checks out. I think that's the answer. Questions?
So, when the pressure goes down, why does the volume go up?
So again, think of pressure as basically a measure of how many times and how hard these molecules, these little gas atoms, how many times they're hitting the surrounding. If the pressure goes down, that means they're not hitting the walls that they're surrounded by very often, right? Or not as often. Why are they not hitting the walls as often? Because your volume got bigger. Those walls spread out further. So your volume, whole bunch of, not a very big volume here, whole bunch of molecules traveling around, they're hitting the walls often. So you have a small volume, lots of pressure, lots of times those molecules are hitting the volume, the sides. As this happens, your volume's getting bigger. All of a sudden, those things aren't going to hit the walls as often, right? It's not as many walls to hit. They're spreading out. So inversely proportional. Cool. Good question. Other questions? All right. Very good. One more law today, then. It's a bit of a doozy, but hey, actually, I already kind of learned the whole thing already. The combined gas law, which is exactly what it sounds like. All three variables all together. Look, we learned that one. We just learned that one just a minute ago. P1 times V1 is equal to P2 times V2. Yesterday, we said P1 over T1 equals P2 over T2. It was Guy Luzak. And we also said V1 over T1 is equal to V2 over T2. So guess what? All three of your rules are all right there, exactly like the name of it says, combined. It's a combined gas law. All of them can work together.
What's the third one?
The one we just learned, Boyle's law?
No. Oh. I mean, no, not that one. The second one. It's P1 over T1 and V2 over V2, and then the second one.
V1 over T1 and V2 over T2?
Oh.
Is that the one you're thinking of?
Yeah.
That was Charles. Charles's law. Charles worked with temperature and volume.
That's Charles, and then the other one was V.
Yep. All right, so example of the combined gas law. Yeah, it's a bit of a doozy, but a little practice gives me perfect with it. So a gas at 155 kilopascals and 25 degrees Celsius has an initial volume of 1.00 liters. The pressure of the gas increases to 605 kilopascals as the temperature is raised to 125 degrees Celsius. What is the new volume? All right, well, again, guys, it helps to list out your variables. This one here, kPa, we should recognize that as a pressure.
So we're going to have like more than one answer on this one?
No, I'm just looking for one thing, just the volume. T1, okay, at 155 kPa, it's got a 25 degrees Celsius temperature. Here's the thing, can we use 25 degrees Celsius?
No.
Yeah, you should all be aware of, no, we cannot. You can't use Celsius. You must add 273 and convert it to Kelvin. And we have an initial volume of 1.00 liters. All right, I'm going to go back in. I'm going to find my second pressure. Let's see, the pressure of the gas increases to 605. Okay. So there's my second pressure. And the temperature raises to 125 Celsius. And we cannot work with Celsius. So we must convert it to Kelvin. To do that, just add 273, pretty simple. Finally, what is the new volume? So our second volume there is unknown. All right, so that's what we're trying to solve for. Whenever we have all three variables, pressure, temperature, and volume, we're going to need to use that combined gas law. So there's that P1 V1 divided by T1 is equal to P2 V2 divided by T2. Again, we're looking for V2. Guys, don't put numbers in there. Don't do it yet. Isolate that variable first. Tell yourself how you're going to solve that problem first. It'll make it a lot easier long term. All right, let's see. We need V2 on a side by itself. First thing, let's get T2 out of here. If it's divided by T2, the opposite of divided by is times. So let's say T2 times P1 times V1 divided by T1 equals P2 times V2. Cool. Halfway there. Next up, we got to get P2 out of here. Right now we're multiplying by T2, so the opposite of multiplying by P2 is divide. And there we go. We have everything set up. We have the one variable we're looking for, that's V2. He's on the side by itself. Now we can go back in and put our numbers in, and we don't even have to, think about rearranging or what gets multiplied because it's all right there for us. It's set up, and we're ready to go. So let's see, my second temperature. Well, hey, I listed it out. I don't have to go back and get confused and try to reread the problem. I made a list right here. My second temperature, 398 Kelvin. You must put Kelvin. If you don't put Kelvin, guys, you're not going to get very many points on this homework. Not even doing partial credit if you can't give me units. So write your units in there. All right, 398 Kelvin times our initial pressure, P1, 155 kPa. Times, looking for V1, and I listed that out, 1.00 liters. All right, all of that is divided by P2. Let's see, that was 605 kilopascals times T1, 298 Kelvin. Cool. Now we are ready to solve. Hey, watch this, watch this, watch this. This is a huge mistake. People make it all the time. All the time. So let's see, 398, cool, times 155. That part everybody gets. Times 1.00 divided by 605 divided by 298. You guys see that? People mess that up all the time. They see the multiplication symbol and they hit times. But guys, 298 is on the bottom. You have to divide it by. If you really want to enter in your calculator exactly like you see it right here, that's fine. You need to put parentheses around it in your calculator though. So if I really am dying to enter it as I see it, I need to use parentheses. There, now I've got the time symbol, 605 times 298, but it's inside of parentheses. That is a huge mistake. I would say in a typical year, more than half of students make that mistake, more than half. A majority of people do it right like that. So if you are planning to use the times button, make sure you have parentheses around those last two numbers. Otherwise, oh no. You can just hit divided by. Then you don't need parentheses. It's on the bottom. You're dividing by it. There we go. There's our answer. 3 significant figures, 3 significant figures, 3 significant figures, 3 significant figures, and 3 significant figures. Sounds like we're going to use 3 significant figures. 0.342. Those are 3 significant figures. The 1 afterwards is not enough to round up. So we'll keep it there. Okay, let's double check. Everything cancels out. Kelvin cancels out. That's good. Kilopascals cancels out. That's good. We're left with just liters. That's excellent because we're looking for a volume. And liters is a measure of a volume. Cool. Questions? Comments? Concerns?